with the it's our pleasure to have you here. So thank you for accept our invitation. We have, I don't know if Miguel told you, he's here in Brazil because of Miguel, you know, the Portuguese guy. And they have a project together. And Miguel asked me if you would like to bring him to the file, and of course I said yes, sure. And he is in Campinas now with Miguel and another colleague that work with them. So we have you here, usually we have this time for our graduate students that someone is doing a speech every Tuesday at this time. So we can have around 1 hour and more, and then we have time to work, to talk. So usually it's 2 hours in a total. Okay? So thank you very much.
Okay. So thank you very much for the invitation. I'm going to tell you about an initiative that I've been involved in Denmark. I'm not sure. About further education for high school teachers to help students who have difficulties in mathematics. I'll give you some background and some examples of the students' learning difficulties from literature, how we designed this program and structured it, what kind of literature from mathematics education that the teachers were reading in the course, and I'll give you some examples of the difficulties that the students they work with have in practice, and some effects, reported effects from the program. So the background. In 2013, so Denmark is a small country, particularly for 5 million people, maybe 5.5 million people. Still, in 2013, we saw the largest number of students in high school, upper secondary school. 7 out of 10 in a generation chose high school. So, and it used to be a long time ago that it was maybe only 15%. And when I was a student in high school, it was maybe 40, 50%. But now, 70, maybe 75% of the generation goes to high school. So in Denmark, when you graduate from 9th grade, you can go out and get an education in vocational education, become perhaps a carpenter, a mason, or something like that. So this means, of course, that the students who go to high school now, they are not all equally skilled in mathematics. So the teachers are experiencing that the kids have new difficulties that they were not used to dealing with. So that was the reason for designing this program. And those who took and followed this program would become math counselors, we called them. And the focus was to not counsel their colleagues, but to counsel the students, to help them to somehow overcome these learning difficulties that they have by drawing on available research findings from mathematics education. Mathematics education as a field is now 50 years old, right? Approximately. So there are some findings about student learning difficulties that could be put into practice. And then devise some instruments for detecting students' cognitive difficulties and their possession of mathematical competencies. In Denmark, the mathematics programs are structured around a set of mathematical competencies that we want to develop with the students. Problem-solving competency, modeling competency, representation competency, communication competency, etc. the target group of the students in the schools were those who were unsuccessful in learning mathematics, but were interested in getting help. So it was not a matter of motivating students who did not want to be in the mathematics classroom, because that's a different pursuit. It was about helping those students who wanted to learn mathematics, but for some reason could not manage to do that on their own. And experience tells us that in every mathematics classroom there are a number of such students who try their hardest to grasp the math they are presented with, to figure out what is going on, but seem to be getting nowhere. Often they make up their own rules, right? They invent their own rules too. But we'll see examples of this. So as I said, it's not a matter of motivating the unmotivated students. That's something else. So this is a number of names of people involved in devising this program. It's maybe not so interesting for you. So let's have a look at some of the learning difficulties in mathematics that we know from the literature. And I'm going to give you some pictures and you tell me what is wrong. So why would students think that these things are equal? Because they do sometimes. You need translation into Portuguese?
Because they think it's a multiplication?
Yeah, exactly. They think there is a multiplication sign there. Sometimes there are, sometimes there ain't. How do you know if there is or not? Yes? So it's a general problem of mixed numbers, and it's one related to mathematical conventions that we often not explicate to the students, right? They have to guess these conventions themselves. This one? Yes?
15 is bigger than 2.
Yeah, exactly. 15 is bigger than 2. So, you need to have an understanding of the precision system, of course. It's not so surprising to us. But there's a lot of reported difficulties in the literature on students' problems with approximation and rounding off, etc., etc.
The answer is that maybe because there is more
Numbers.
0, 3, 1, 5.
Yeah, it could also be that there are more integers on one side than on the other. Could be the 315 is like in 2. Some students believe this to be an irrational number. Is it? No. So, a colleague of mine had an undergraduate student at university who told him, well, on the one hand, she knew that this was equal to 3. But on the other hand, it was, and 3 is a rational number, but it is also an irrational number because there is the square root. And how could this be? Because he had just told him that a number could not be rational and irrational at the same time. So the thing with the signs here can also confuse. So there is a large difficulty with fractions, rational numbers, etc., etc. This one?
Because 5 minus 5 is 0?
That is of course true, right? So it could be a mistake if you think that something lifted to the power of 0 is actually 0. We know that it is not. But it could also be that, I mean, you know that And then you just start, right? It's a process. There's nothing left. Nothing to do. So this is a finding that has been reported by Alan Schoenfeld many years ago. And students who may answer this are students who can perfectly well find the answer to this question here. So if you ask students what they can say about the relationship here between y and x, what might they often say, do you think? They quite often answer that x is 5 bigger than y. There are 5 more, right? On x is 5. Even if they are capable actually also of sketching a graph for this and seeing that this is not the case. This is another example from literature. So we know that for many students it's difficult if x is on both sides of the equal sign. It's much easier to solve equations where the x's are over here on the left-hand side. But this particular study from '93 showed that students who were perfectly capable of solving this equation and finding the solution, when they were asked afterwards, can 10 also be a solution to this equation? They said, I don't know, maybe. So there's a lot of difficulty with the students to solve the equations, yes, but also understanding what it means to be a solution to an equation. Right? And if you think about it, how many of you have taught in school? Mathematics in school? Not so many. Okay. How many of you have taught mathematics at university level? Not very many. You don't teach. Okay. So, but when you taught at school, did you, when you taught at school, did you give your students the definition of what an equation is?
Yeah,
You did?
I think so. But I think everybody has teach once before. Ele perguntou se alguém já deu aula em escola. Ou se alguém já deu aula na universidade. Pois, né? Devia responder.
Todo mundo tinha, ninguém deu aula de nada.
Okay. In Denmark?
Everybody here teaches.
Okay, they do teach it.
Before,
They
right?
just don't
Just
want
shy
to,
with me.
don't want to admit it. So, but quite often, in Denmark at least, students they have to solve a lot of equations, right? They have to solve a lot of linear equations, but they're never presented with a definition of what is an equation. So, a lot of students think that this is not a function. Why? Do they think that? Yes, why? Because there is
No X.
exactly right. But it is it's a very well-defined function. A lot of students would also think that this is different from this. Because often functions are associated with their expressions rather than their values for students. Right? And this one is just beautiful, right?
Wow.
Yeah. Okay. So this is what Danish high school teachers see on a regular basis. Right? There is another one here that's kind of fun, maybe. So this is a study from Israel, reported in several papers and done on different occasions, etc. So there's a class of high school students that are introduced to a proof that 6 divides n to the power of 3 minus n, where n is a natural number, with no remainder, right? Did any of you know the proof?
Mas a gente não tem esse prova muito, né, no SMEM.
Não.
We don't have this kind of proof in high school,
No.
like usual. Maybe some schools do it, but
Okay.
we have here, I teach it first year here, when they start the course, but I'm not sure if not as a regular curriculum, maybe some teachers can do it.
Okay. It's just a nice little proof. So you do a rewriting of this, you put n outside the parentheses, then you realize that this can be written as this, okay?
Yeah.
Then you reorder these, and you see that this is the product of 3 consecutive natural numbers. Hence, one of them must be a multiplication of 2, and one of them must be a multiplication of 3. Hence, 6 divides with no numbers, right? Okay. So, but the didactic perspective is that in class it's introduced to this proof. It's a general proof, right? It goes for all natural numbers. And then the next day they come back and they ask them about this one. Does 6 divide this? No. And then the kids are split into 3 groups. There are those who say it's from yesterday, but they are confused that yeah, we know this because we proved it in general, and now n is just equal to 59. Then there are those who just do the calculation here on the calculator. And then there's this group who repeats the entire proof here, but with 59 on nth place. So those students have not understood what it means to prove something generally. Right? What are the consequences of having provided a general proof for a statement of mathematics, right? And in many high schools, you need to know that. So, these learning difficulties that we talk about, they are not this dyscalculia kind of thing. It's not that. It is not that. Because that's only a very small population, a percentage of the population that have these difficulties, and they are more neuroscience kind of like. So we're thinking about student learning difficulties of math in relation to difficulties with mathematical concepts and conventions, right? Difficulties with mathematical reasoning and proof, mathematical language, mathematical model for modeling. Okay, are there any questions so far?
I have one last. This you put here is something that I have on a reference.
What?
Like this, everything you put before, you have one name in the end, that is the name of the author, and here. This is something you have on a
No,
paper.
this is our, yeah, we have our own thing.
Yeah, you
Yes.
have yours, right?
This is ours. So, okay. So the idea was to design a program for further education for high school teachers to assist students with difficulties like these. How do you do that? Well, you need to have some considerations on having a balance between theory and practice. So, the program can't necessarily not be based solely on teachers' own experiences and intuition, because in such case, these difficulties would not be there. They would have been resolved already in practice. It must base itself on some findings and experiences from research, some theoretical constructs from mathematics education research. And at the same time, these research-based findings and experiences must be transformed into practice. Quite often when you do such further education of teachers, they go to the university, they are presented with a lot of studies and a lot of theory, and then they go back and they think, well, right? So they needed help to transforming this theory into something they could actually use back home at the school. So that was a considerable consideration when designing this program, how to do that. So there needed to be a balance, simply, between the theoretical parts and the empirical, practical empirical parts. We wanted the teachers to work with students, right? That's part of the program. And we wanted them to work with students who had learning difficulties like these, like the ones I showed you, right? And this was also a way of gaining actual experiences and training for the job of being a math counselor afterwards. It's a way of putting theory into practice for the teachers, right? And when the teachers were done with this program, we wanted them to be able to find students with learning difficulties in mathematics, determine in what these difficulties actually consist. Are they difficulties that are related to poor concept formation regarding some mathematical concept? Is that maybe they cannot solve linear equations, right? But there can be 100 different reasons for that. Maybe it's because they have difficulties with negative numbers and they will not accept negative numbers as solutions to linear equations, because in the textbook they had back in primary school and secondary school, all solutions to linear equations were natural numbers smaller than 2. It's not uncommon that this is the way it is. And we wanted to enable the teachers to do something for the kids, right? To do something to help the students overcome these difficulties. So the structure of the program was 3 semesters, 3 themes, 3 phases, and 3 tests. These teachers, they couldn't come to the university every day, right? Because they were teaching in school and some of them were far away. So once per semester, we went to a place where we taught them and we stayed there for 2-3 days, right? 30 ECTS, the European credit system. We had to do 3 mini projects. There were 3 courses. They got a list of literature for each semester. I will explain this to you in a minute. And they did some empirical work, and this had to take place on site at the school. And there was finally saying at the very end of the program where they got this. And the 3 themes was concept and concept formation in mathematics. Right? This, most of them could relate to this, the students that did this. It was more problematic for some of them to understand why we had to discuss reasoning, proofs, and proving in mathematics. Because if they didn't know the concepts and they couldn't solve the linear equations, why do we need to talk proofs and reasoning, right? But if you take reasoning and proof out of mathematics, what's left? It's calculation. It's not really math. And also, if you are actually able to reason, maybe you can think for yourself why you are solving these equations in the way that you have to do. Right? So, being able to reason and prove something can assist you in concept formation. And then models and modeling in mathematics, because this has always been a part of Danish high school, but a lot of the teachers are not trained in this. And there's a lot of didactic studies about this. So they did these mini projects together in small groups, and each mini project needed like a problem formulation or like a research question. For instance, it could be what are the connections between student A's beliefs about mathematics and proof schemes which he possesses. Proof schemes, have you ever heard about that? It's a study by some Americans that talk about what is it actually that convinces you that something is true. And it can be either some external proof schemes, it's true because my teacher Ruby has said it was true. Or it's true because I have tried with 5 numbers, and it's good for all these 5 numbers, so probably it's true for all natural numbers. Or then there are the actual deductive proof schemes, right? But there are different kinds of things that actually convinces the student that something is true. And they need to hand in these projects, actually. And then there were the 3 phases that they needed to go through with the students. They needed to identify these students, and for that they designed some research-based detection tests that they could give to classes and look at and analyze and see if there were students who had some kind of difficulties. But you cannot say where the difficulties come from, where they originate from, just based on the test. You need to talk to the students. Right? So in order to make this diagnose, they needed to interview the students about these difficulties. And then they needed to design some kind of interventions to help the students overcome these difficulties. Now, the mathematics education literature has a lot about the types of difficulties, and it has a lot about what might be the cause of the difficulties, but very, very little about how to help the students go further. And this, of course, is to do with the fact that the teaching of mathematics around the world is very different, right? So what might work in Rio, Brazil may possibly not work in Copenhagen, Denmark, right? Because students are different, they have different schooling, they have different. So here the teachers had to come up with some things themselves, but they could, of course, use the research to design their interventions.
One moment, please.
Yes.
Só para ver se todo mundo acompanhou, né? Na verdade, eu me perdi uma parte. É um curso para professores, não é isso? Mas não, é um curso de formação continuada. Não são revistas que entendemos tudo. Não sei se todo mundo está acompanhando aí, né? Ele, acho que vale a pena recapitular rápido. Então, ele fez esse curso e ele acredita, ele falou um pouco no lado do almoço, ele acredita muito nessa relação entre a teoria e como é que a teoria, né, como é que a pesquisa chega na escola e como é que a escola chega na universidade, né, nesse diálogo. Então, ele usa essa prática dele aí, né, com esses professores para tentar fazer essa interlocução entre a teoria e a prática. E aí, então, ele está descrevendo, né, eu acho que todo mundo acompanhou as coisas que ele está apresentando. Tinha que fazer 3 grupos, né, 3 fases. Para variar, assim, eu quero chamar a atenção, né, que eu tenho uma coisa que eu tenho visto bastante, não sei se todos têm reparado nisso ou se é uma percepção minha, mas eu tenho visto muito nos eventos que eu participo internacionais essa preocupação com que a gente aqui no plano tem um pouco diferente, né, assim, a gente quase não faz coisas com testes e com quantitativos, né. Isso é uma coisa que tem me chamado muita atenção nos últimos anos. Quase todos que eu vejo, assim, né, quando vou nos eventos, eles têm uma parte quantitativa, uma parte qualitativa, né, e fazem esse famoso quality e tal. Vamos esperar ver se é isso, né, esse detalhe eu não conversei com ele no almoço. Mas eu estou destacando porque daí quando ele for falar, né, se vai nesse viés mesmo, a gente prestar atenção nesse caminho, que não é uma coisa muito usual aqui no plano, né, ao meu ver, assim, eu conheço muitas pessoas do plano. Thank you.
Okay. So these detection tests that we designed for each of the semesters and each of the 3 themes were, the first one had questions on mathematical concepts, conventions, symbols, the concept of number, function, and algebra. And the second one had questions on argument, proof, and reasoning, the differentiation between students' ability to understand the question, reading, do the involved mathematics, and follow the logic structure involved. Right? Some students can actually follow the logic, but they can't do the math because they don't know the math. Other students can do some of the math, but they cannot follow the logic. And finally, this down here was the various processes of the so-called modeling cycle. And in this one, we were able to use some old tasks from the PISA assessments because back in the day, they were based on mathematical modeling of the tasks. And of course, the names of these tests is a play on this saying 20 questions for the professor. Now it's just a bunch of questions from the professor. So, what kind of literature did these teachers have to study in order to be able to do these things back at school? For each semester, they were provided with 3 literature packages. electronically in some files, general literature, specific literature for the theme, and some supplementary literature. And they had to read these general and specific literature, and they also had to read each other's mini project reports. So over this 1.5 years, they probably read 1,500 pages of mathematics education literature. So the general literature in the first semester was on instrumental and relational and logic understanding by SMEM. Are you familiar with this? It's an old classic from the 70s. You can have instrumental understanding. It means that you know what to do and how to do it. Right? So for instance, you can divide two fractions with each other. You know the procedure of doing it. You can solve a linear equation. You know the procedure of doing that. But you need not necessarily have relational understanding. You need not know why, when you divide two fractions, you multiply with the opposite. You need not know why you do what you do when you solve linear equations. You can solve it anyway, right? You don't have the understanding of knowing that you respect actually the equivalence of different signs. And every time you do something on one side, you must do the same on the other side. So this paper talks about that. Then there's an old paper by Danish on process and object. This here was a process, right? And we get lost in the object. The object is this. And it is in fact the number 1, right? Concept definition and concept image by Tall and Winner. It's a paper that talks about, for functions for instance, right? You can have a concept image of a continuous function, something that runs like this very smoothly. But it's not necessarily the same as the concept definition, because the concept definition of continuous functions will also include something that runs like this. It's just very awkward, but it is still a continuous function. And then the report on competencies, and Val has a very nice paper on semiotic representations, how you shift from one representation of something into another. For equations, for instance, it could be, or for functions, it could be the symbolic representation, a story that is a verbal story connected to this, and then a graphical representation. And when you do these shifts between these registers, this is actually an indication of you possessing some kind of idea about this concept. Right? So you can use this both to diagnose what difficulties the students have, are there some transformations they cannot do, but also to design the intervention saying, we need them to make this register shift because they have these difficulties. And some specific literature. In the second semester, about this thing with proof schemes, social mathematical norms, it's called. You know this construct? Social mathematical norms. There's something in the classroom among the students that become taken as shared, and it also has to do with the interaction with the teacher. What will the teacher accept as a good enough solution, a good enough argument to a certain task? This varies from classroom to classroom, right? And it's not always the same as the mathematical norm. Beliefs about that you are not good at math, or beliefs about problem solving, mathematics, etc. Didactical contract. You heard about this from Prof? Yeah. There is a contract between the teacher and the student. The teacher expects something from the student, and the student expects something from the teacher. And sometimes you have to make a new contract. So for instance, when these teachers have to work with these students who have these difficulties, then the students will actually need to show the teachers what they were and were not capable of doing. And a lot of them would be afraid of hiding this because they were afraid of getting a bad grade, right? A bad mark from the teacher. So they had to establish a new didactical contract saying that what they did in this room with the math counseling did not affect the grades that they were getting in class. So, or that the math counselor would not tell the teacher. And then there are these things about different roles of proofs, etc., etc. There are proofs that prove the theorem, and there are proofs that both prove and also explain why the theorem is true. And sometimes the latter one is very long to do. And a bunch of stuff on modeling, right? And also modeling related to technology. Let's maybe not go into that some. So let's see some examples of what the teachers found among the students, the difficulties they had. This one here is just one of my favorites actually. So it says solve the equation 6 times s equals 4 times s plus 1. Okay? So the student writes here, the first that I'm thinking is to isolate s. That's a good one. It's not bad. Then he writes up the equation here. And even though this is actually a multiplication sign, he subtracts 6. Right? You see it over here? Then he has this, and this s here goes on the other side. It does not affect any of the other. Then he can calculate this. Of course, s divided by s equals s is not uncommon. And the argument for the student is, but where else would s go? Right? You can't do it. And then he ends up with s equals minus 1. But this student actually knew that you could take this and plot it into the original and see if it was true. So he found out that it wasn't. A lot of the students, they forget that. Also from using technology, they forget that you can actually test if the solution, if the found solution is the solution. This one over here is also quite interesting. So it's a second degree equation. Solve the equation x squared minus 4x equals 0. And this student knows that this squared thing is the nasty thing and we want to get rid of it. So he takes the square root of only this. It's like a circle operation. Only this string. And yeah. So he actually ends up with one of the right solutions, but by mistake. And so these are some of the things that the high school teachers, they were dealing with in practice, right? And they had to help the students see what the mistakes were and why. So here's another one with the equation and number concept. There's one student said very explicitly that I cannot say 3x minus 1 because I can't subtract 1 from x. You can't subtract a number from a letter. If there are the numbers you can do math with, and there are the letters you can do math with, and you cannot make the two make no sense. One student could not do this division, 24 divided by 6, I don't know, when the numbers are so big. The reason they were big was because she couldn't use her fingers anymore. And this is a student in second year of high school, right? So the central obstacle for equation solving is an underdeveloped concept of number quite often for these students. With functions, you know, they would look at this and they would say, well, x is the unknown, and y is y. Or y equals 2x plus 5, then they look at this and they say, well, then x is 2. And since this is gone, there's only 5 left, so y must be 5. And the teacher said, so can you sketch that for me in a coordinate system? Sure thing, it's the point 2.5. Do you understand? Yeah. So that may be really difficult to provoke. So what this thing about concept, image and concept definition, this theory talks about cognitive conflicts. Have you heard about this? If there is a discrepancy between the concept definition and the concept image that we have, you must bring the students to realize this, then there can occur a cognitive conflict, and they may want to resolve it, right? But when the students have these many difficulties, it may be quite difficult to actually provoke these cognitive concepts. So here's one with these, some of the questions from detection test 1. The students get this one, same one is over here, right? They get this one, and they get this one. And if they say that they are all equal to 0, then you have a sense that there is some kind of misconception here that is consistent. And if the students' misconceptions are consistent, then they're actually much easier to work with and do something for than if they are completely random. So this, although it's not good, it's actually much better than if it had been something different all the time. But it also has to do with the fact that the students seem to have a difficulty with the number 0, right? A lot of students would say, if they got an interval, -2, -1, 0, 1, 2, and you say which are the numbers here, they would claim 0 not to be a number. Often. For many of the students, 0 is not a number. It's a placeholder for the absence of a number. But 0 is a perfectly fine number. You can just divide by it, other than that. So, okay, so they have to design some of these interventions for the students, and sometimes it went really well, but not always. Right? So, there's this thing with Mary here, and I was visiting the school that day and seeing the teacher work with these 2 students, and one of the detection test questions was, is a squared equal to 2a? And this student, Mary, she's a 3rd year high school student, she says, yes. It's just another way of writing it. This is it. So the teacher asked them to try to put 2 into a's place. And they say, yeah, you see it's the same. Because you're supposed to say 2. Then they try with 3, and they say, okay, so it's not the same. It's only sometimes that it's the same. Okay, but when is it the same? Then they think about this for a long time. She says, so only when a is equal to the power. So only when a is equal to this number here, she thinks it's the same. No. And then she says, she realizes this is very difficult for her, and then she said, maybe it's because we are thinking about differentiation. But there was nothing about differentiation. It is of course true that x squared differentiated is 2x. So it's not her problem with the simples not being x, but she simply is not really knowing what we are doing, right? And never does she realize that this is a 2nd degree equation in A with 2 solutions. That never occurs to me. So then they continue, and after having calculated some smaller things such as a to the power of 4 divided by a squared, etc., they are asked, so what is a to the power of 100 divided by a to the power of 10, and what is this one? This is our friend. Mary says, well, isn't it just a, well, they cross out. So here's only a left. Or 0, since they cross out. But a has to be there still, right? So it's the same thing as with the s before. It can't go away, it can't disappear. It has to be there. Where does it go? Then this teacher, with this particular student, Mary, had another session with her where they did the proof of the Pythagorean theorem, right? And it was written like this. You all know what I'm talking about, right? Do you all know what I'm talking about? Otherwise, I will just say that a bunch of gibberish. So they had to prove the Pythagorean theorem. And then they did this slowly, step by step, and she agreed to every step and was able to follow it. Then the teacher said, okay, now we're going to switch the symbols. And he also did it on the drawing, right? He switched the symbols so that the hypotenuse were now called B instead of C. And as you can see, with only it's the same triangle, it's the same thing we're going to do. I'm just calling it something different. They do the entire proof again. She agrees to every step. And at the end, he asked her, so is this correct? And she said, yes, you just have to change plus the muscle. So she still thinks that this over here comes from over there, and it's the same, it has to be the same. She didn't get the idea of what was going on with this particular group. They designed another intervention for Mary. And this was an intervention where they had to, they wanted to force the students to reason. And they thought, okay, if they can, we can ask them about the number of diagonals in these polygons. So you see here there are 2 diagonals, then there are more diagonals. What is the relationship between the degree of the polygon, the number of sides, and the number of diagonals? That's what they wanted them to reason about. But the question they asked them was just find the number of diagonals in these polygons, and when you're done, you can go to lunch. So many of the students, they would come up with the formula for this, but not this girl Mary. She actually started counting, right? And you can see that here she has small marks, right, counting, and then it becomes, she can't see the marks, so she starts drawing on top of them. And of course she's not able to count correctly. So that the teachers, they conclude, well, she is not alarmed by the cognitive conflict which her concept images constantly must initiate. Instead, she accepts that there's a new arbitrary rule that must apply here every time she's doing some kind of math. The only thing consistent in mathematics for her is the inconsistency in the subject. She was asked also, where does mathematics come from related to her beliefs? She said, I always perceive mathematics as a collection of rules you have to follow, and that's just the way it is. And the teacher says, is it the math teachers who come up with those rules? She said, no, it's the philosophers. Isn't that what they're called? So it's for this student Mary, and I think she's unfortunately not the only one in Danish high schools. Mathematics is a collection of rules, right? Arbitrary and not related. And sometimes we're differentiating, sometimes we're equation solving, as if we are, maybe today it's one, or maybe today it's the other, but there are only very few rules in mathematics, right? And you can reason the rest of it. So, she was an example of when some good interventions, well-thought interventions, work for a bunch of students, but not for her. So you cannot help all students. Right? Okay, but some reported effects from the teachers. The teachers say that the literature offers less in terms of intervention, this we know. But the teachers devise different kinds of interventions based on the specific students' difficulties, as well as their own expertise. They have small group sessions, sandwich sessions with students. They come and get help and get a sandwich. Individual sessions, especially devised tasks, etc. Classroom interventions.
What is sandwich session?
A sandwich
Yeah.
was like a name, right? So they would help the students during lunch, and the school would give the students a sandwich. So they would come and get help with mathematics. Yeah. Because the school wants the students to pass, but because the more students that pass, the more money they get from the government. So this student actually got a middle grade, the one with this, and this student moved to the front of the classroom. Mary did not come to understand a lot of mathematics, but she did pass it. at third grade. They were able to teach her that and help her that. Some of the teachers' own reaction to say that, well, changing role to not being a teacher and letting students explain themselves has provided an insight. So we would go to the schools and observe the teachers while they were working with some of the kids. And one of the very difficult things for them was when they were interviewing a student about something that he or she did wrong, and the student would do the task on the blackboard or something, and then when the teacher saw that now they were going to do something wrong, they would say, no, remember, we always use this rule. But as a math counselor, you can't do that. Because maybe what they are going to do, the wrong thing that they're going to do, is what will show to you the origin of their difficulty. Right? So this was difficult for them. It was a new role as a math counselor, not math teacher. And they thought that it actually made sense to use these theoretical constructs. Right? If you remember these quotes from these teachers who work with Mary, they don't just say, as they would do before, forget about Mary, she can't do math. We're not going to teach her anymore. Now they say, well, she does not get these cognitive conflicts. Right? The rules of mathematics are not consistent. So from the literature that they read, they have developed a vocabulary that they can use to articulate the nature of the difficulties that Mary has, which will assist them in designing some interventions that could potentially help her further overcome these difficulties. They also realize that it is extremely difficult to actually map students' difficulties, right? And that learning is not a linear process. But what often happened to some of these students was that if you found somewhere where things were a mess for them, solving of linear equations, that you can assist them with this and they figured out something, then maybe some of the bricks further down in the construction of mathematics would also fall into place for them. They also said that students must be faced with much more difficult tasks in order to provoke them to begin to provide arguments. And one teacher said, I now tell more about what mathematics is, and it seems to create an interest. I have become more observant of students' beliefs and of what I tell them. Our approach to teaching is often example and not proof, which is reflected in their perception of the subject. So, this was not the purpose of the course. The purpose of the course was to enable these teachers to become math counselors, to help the students get a passing grade and understand some math. But as a consequence, as a by-effect, they also changed their own teaching sometimes. So one final example here that came out of this, of the teaching on this course that we hadn't seen in the literature is what came to be known as the MV interpretation. So, so these teachers found a student and they gave her this formula for linear functions, right? And then she was to explain what y is, and she of course said y is b. What is x? X is a. The same idea as before. A is next to x, so that's what it is, and this over here, then that's what's left, so y must be b. Explain what a is. A tells you something about x. Explain what b is. B shows you what y is. Okay? So they're looking at this one again. She's saying y is a number which we do not know. No, x is a number which we do not know, and that's because there's no a now, right? There's nothing in front of x, so we don't know what x is. And y is 5. Explain how y equals 2x plus 5 is different from this one. X now has a value. X has a value here. And then the student is also That's before able to draw these things, right? It's the point here. We do not know x, hence we say that, that's what it says over there. Hence we say that x is 1, since it is not to be the power of 2 or it's multiplied, then x is gone. Then y is 5, and we can place the point. The other point is 2 points. You're asked also to explain how this point is put into the coordinates. So for them, this thing, it's not a line, it's not a linear function, it's just a point. So if you have this perception, then there's a lot of things in the first year of mathematics in high school that, I mean, is going to go like this for you, right? Because you don't know what you're talking about. So knowing this, these two teachers were actually able to assist Emily through a number of these lunch sessions that I talked about. And they were able to make her pass. And what they further did was that they did a test of 417 newly accepted first-year students at their school and found out that 9% of these had an interpretation that resembled that one of Emily. That's pretty freaky. And it was quite a bit of a surprise for their co-teachers at the school. But it could explain some things. Okay, so some final remarks about the program. We have educated 70, so remember Denmark is a small country, we only have 3 million teachers. So we have educated 72 of these math counselors. We have 200 high schools in all of Denmark. And we are educating 14 more this semester and next year. And the thing with these teachers is that they go back to the school and they now have all these theories in their backpack and all this language about math education and difficulties. And it's difficult for them to talk about this in the same way with their co-teachers at school as they would do with other math counselors. So we have devised an annual meeting where the educated math counselors, they come and meet the new ones who are under education and can talk to each other about how they're working at school. And then we usually have an invited guest speaker. So some of the people whose papers they have. So we have had Helen Dorr from the US, Aaron McKieran from Canada, Tommy Dreyfus from Israel, also a Danish guy, Von Blomberg, and Raymond Duval from France. So this is quite interesting for them and for us. So some conclusions that, I mean, what this shows is some kind of existence proof perhaps, that math counselors can make a difference for students if they manage to make somewhat correct diagnosis of the students' difficulties. They become better at this over time, of course. And the math counselors all report changes in their own teaching practice as a positive byproduct. And the math counselors point to having developed a language and vocabulary enabling them to articulate the various difficulties of their students, which they were not able to before. They would just say, Mary, can't do math. That's not how they articulated it. So maybe all in all, this model for the program appears to work. And that's what we saw with this presentation, that how this program was actually designed appears to be one way of doing this. So this could give rise to some new research which will impact the future implementations of this course. We have around 1,000 detection test answers from students that we are looking into. And although there are some cultural aspects of this, I mean, some of these stumbling blocks that we have seen are not specific for Denmark, but rather international, right? And they're also reported in the international literature. So maybe the model can be transferred to other educational levels, countries, etc. And we've been able to publish a couple of books where chapters, in Danish of course, where chapters are written by the math counselors about the students they work with during this education program. So thank you for not falling asleep on me.
I have one to start. Can you put in that slide I asked you about the reference, please?
Which
paper, not a
Yeah,
marker.
okay, that's what it's
I will ask you, just for curious, and of course I'm thirsty, is, you said you did this with numbers, functions, and algebra. Yes, this one.
Yeah.
So I ask you, first question is why this subject, not geometry, for example,
Mhm.
or data, statistics, don't say just
Yeah.
my thirsty. And if you think this kind of problems or difficulties of the students, if we can generate or think about this for geometry. You think if I do the same you did, as you put in the last slide, okay, try to another level. I would say I would try to another subject.
Yes.
Do you think I will find similar, or what do you think?
Yeah, I think we will find some similarities, but the reason that we're doing this is because, I mean, so there's not graph theory and there's not complex numbers because this is not part of the curriculum, right? And geometry comes into play better, we thought, in relation to reasoning.
Yeah.
So there's a bunch of geometry in the second detection test.
So you consider it?
Well, it was just a more, for the detection test, it was a better place to have it. And some of these, yeah, we don't have a bunch of questions about geometry in relation to concepts and
Because
operations.
when I read it, it for me looks the same. Maybe I can find one
Yeah,
more
yeah,
line,
probably,
then okay,
yes,
probably
yes.
I would find problems with concepts, with language, with
Yeah,
reasoning.
and you could continue to this, I completely agree, yes.
Okay.
So,
Alguém quer perguntar alguma coisa? I told them when I stopped at that time that usually I see in conference, and especially when I go to an international conference, and like a study, quantitative and qualitative study analysis.
yeah.
So when you start that, say you have questionnaires with
Yeah.
so I told them, probably we will see this, and I'm frustrated that it didn't bring it, not just because I told them, let's see if it will happen. But you put in the last slide in the end, says, yes, you will write it. And we'll do it. That is, you said this is next steps, right?
Yeah.
So
You-
on this we will do,
You want to see some of that?
I was just curious that you do it, right?
Yeah, we
You
will do
do
something related
quantitative analysis too, not just qualitative, right? But you do both together, or one is one, the other is the other?
No, I think we will mix it. Let me see if I can find
Alguém aqui faz pesquisa PowerPoint? PowerPoint? Não, só tô pensando que eu tô falando. É uma coisa que eu não vejo nunca aqui.
It's not a
Like
secret.
we're doing with this.
It's not a thing.
I just asked them, so here is doing gold. Here we just do. Here we matches.
So this is in Danish, right?
Okay.
So these are some of the questions from the first detection test that the students were given. And I think we have this analysis we have 676 answers, and 405 of these were from first year students, and they were coded by a student of mine, not a student. So this first question reads, does there exist any value for a such that a squared equals 2a? Okay? And of course it does, right? We talked about this before. It's a second degree ratio, you can solve it. 37% get this wrong. Right? This next one says, does there exist any values of b such that 4b equals 4 plus b? 70% get this wrong. It may have to do with this, the fact that it's b. Yeah. 70%, that's quite a lot. This one, this says solutions of simple equations. This one says determine n when this is given. This is from the literature. What quite often happens is that when they are calculating this, they say minus 2 plus 5, that's minus 7. But that's not the case. So 30% get this wrong. Solve the equation 3x plus 20 equals x plus 64. You have x on both sides of equal signs, so this is difficult for the student. We know this from literature. 41%. Solve the equation minus 6x equals 24. The difficulty here is the negative sign in front of 6. 37% get it wrong. Okay. You can get this wrong for numerous reasons. Okay? Let me show you. Some will say that it's 4 because they forget this negative sign. Some will write this. This is of course not completely untrue, but it's not what we're looking for. Some will just add the 2. Minus 6 over here plus 6 over there, that's 30. Some will subtract them. Some will multiply them. And one down here says, it gives minus 4 or 4, but I'm not sure. I can't do the math in my head. I calculated it in my head. Then there are these types of questions that ask what the solution is. They're a bit more nasty. Also in the first test, they say for which x is it true that 38x plus 72 equals 38x? It's not true for any x. So, and this could be explained with this concept image that the students have of these equations. They're not used to being presented with equations that have no solutions. And they're not used to being presented with equations that have all real numbers as solutions. Right? See, I mean, this is not very impressive. And then afterwards, to the same one, see, is 0 a solution to this one? Then you almost have the wrong answers. And then if we look at what they write in this test, so for which x is this true? Here it says both, meaning both for this x and for this x. So this student has not conceived the convention that when we write this in mathematics, then this x is the same as this x, right? It represents the same value. Again down here, one suggests the last x, this x, the one at the back, the one at the front, right? So this has to do with the mathematical conventions. And then this one is 0 a solution to this equation, and one says, I say yes when the equation always resolves. But usually you don't calculate with 0, which is of course not true, right? But it's apparently some belief that the student has that usually don't, like 0 is usually not a solution. And here you have one that can say, to this one, the general one, what is the solutions to this equation? You say, well, this solution can be any value of x, right? Any value of x. It's actually a correct answer. But it cannot be 0, right? It takes the no box. So for this student, maybe it's something, difficulties with the number 0, as we talked about before. Then this is also not very good, because this is a question that asks if A is equal to B, is then B equal to A? And 14% of these 405 students think that this is not the case. Often the equal sign is perceived as a process from left to right. 4 plus 5 equals something. You have to write it. But it is also, and this is sometimes you use the equal sign like that. But the equal sign is also always an equivalent relation, right? And you need to know this, and the student don't know that. So this is going to make it difficult for them in the first year of high school. What is 0 times x? 19% get that wrong. What is 0 plus x? 18% get that wrong. Right? So it's something to do with the number 0 again. Yeah.
But, Prof,
Yes.
what I'm asking is, sometimes, of course we use, like, some of this percentage, como é que fala percentagem em inglês?
Percent.
Percent?
Yes, 10%.
Yeah, but this is not exactly what I'm asking, because this, of course, we use, it's usual to use it here to, like, but this kind of test is a statistic test. This is
Yeah.
what we don't, we're not doing, right?
Yeah.
I don't know the name in English exactly, like teste de quadrados, coisas assim, desvio padrão, sabe? Porque eu quero dizer assim, usar porcentagem para mim não é uma pesquisa quantitativa, entendeu? Não é uma análise quantitativa. Eu trouxe números nesse. Se eu falar por estatística, se daí uma pesquisa quantitativa, o estatístico vai falar que não é, certo? Que não tem aqueles testes, etc. Ainda não sei como perguntar esse é o nome dos testes.
Talvez standard devi.
Oh, standard percent.
Yes.
Thank you.
No, we're not going to.
Oh,
What we are interested in using these tests
just
for
these numbers to
Well,
show.
is to show, I mean, what is
Where
the,
is the problem? I'd say.
yeah, how big is the problem?
Yeah,
And what are the different reasons for the problem, right?
we do it too.
Yeah.
So, no more questions?
I have just it's a curiosity
Yes.
about the schools there. Like the students, they stay the whole day on school. It's only one period of
No.
how it works.
How it works at the schools, you know?
Yes.
In the high schools. No, they go there and then maybe they have math in the morning, then they have gym, then they have biology, they have language, they have that. So they go there from 8 o'clock in the morning to 3 o'clock in the afternoon, like 5 days a week.
Okay.
8 to 3.
Age of the students from 15 to